In this application, we use the subset selection methods covered in this lecture. The R script is application best subset selection headers, and the dataset is headers CSV. As always, the first thing we do is change the working directory to where we saved our dataset. After that, we read the data in. The reg subsets function, which is part of the library libs, performs best subset selection by identifying the best model that contains a given number of predictors, where best is quantified using the sum of squared errors. The syntax is the same as for the lm function. The summary command outputs the best set of variables for each model size. An asterisk indicates that a given variable is included in the corresponding model. For instance, this output indicates that the best two-variable model contains only hits and CRBI. By default, reg subsets only reports results up to the best 8-variable model, but the nvmax function can be used in order to return as many variables as desired. Here we fit up to a 19-variable model. The summary function also returns R squared, adjusted R squared, the sum of squared errors, CP, and BIC. We examine this to try to select the best overall model. For instance, we see that if we use the adjusted R-squared criteria, the best possible model is the model that involves 11 variables. Plotting the sum of squared errors, the adjusted R-squared, CP, and BIC for all of the models can help us decide which model to select. Note that type equals to L option tells R to connect the plotted points with lines. We first start by plotting the sum of squared errors. Next, we plot the adjusted R-squared for all the possible models. The which max function can be used to identify the location of the maximum point. For example, using the adjusted R-squared, we see that a model with 11 variables provides the highest adjusted R-squared. Therefore, we will now plot a red dot to indicate the model with the largest adjusted R-squared statistic. The points command looks just like the plot command, except that it puts points on a plot that has already been created, instead of creating a new plot. See over there, where we have 11 variables. We repeat this procedure for CP. Here is the plot. And then we look for the model that gives us the smallest value for the CP, which is a model with 10 variables. And then we proceed to add a red dot on this plot, which indicates the best model if we look at the CP as an information criteria. Next, we do the same using the BIC. in order to select the models. We see that a model with 6 variables is the best model. We plot the BIC for all of the models with all of the possible combinations of variables, and then we add a point here for a model with 6 variables. If we look at adjusted R-squared as a method for model selection, then the best model was the one with 11 variables. So if we want to print the coefficients, we can use the coef function in order to see the coefficient estimates associated with this model. And we have them over here. Next, we want to perform forward and backward stepwise selection. We will also use the rec subset function in order to perform forward stepwise or backwise stepwise selection. We will use the method forward or the method backward. We can also use the step function, which we'll use in an example later. For instance, we see that if we use forward selection, the best one variable model is the model that contains CRBI. The second two variable model is the model that contains hits and CRBI. Next, we want to see which model gives us the best fit according to the adjusted R-squared, and this is a model that selects 11 variables. Next, we perform backward selection, and then again we select the best model according to the adjusted R-squared, and we see that a model with 11 variables is the best model according to backward elimination. Finally, we compare the coefficients between the full model, the model that used the best subset selection, forward selection, and backward elimination. We notice that in this case, if we use the adjusted R-squared, all of the 3 selection methods point to the model with 11 variables. The best 11 variable models, chosen by forward selection, backward elimination, and best subset, are identical in this case. Next, we want to choose among the models using the validation set approach. We just saw that it is possible to choose among a set of models of different sizes using the adjusted R-squared, BIC, or CP. We will now consider how to do this using the validation set and cross-validation set. In order for these approaches to yield accurate estimates on the validation error, we must use only the training observations to perform all aspects of model fitting, including variable selection. Therefore, the determination of which model of a given size is best must be made using only the training observations. In order to use the validation set approach, we start by setting the seed, and then we split the observations into a training set and a test set. We use a 50-50 split here. Next, we fit all the possible models on the training dataset, and then the model matrix function is used in many regression packages in order to build an X matrix from the data. Now we run a loop, and for each value of I, meaning for each size of I, we extract the coefficients from regfit_best for the best model of that size. Then we multiply them into the appropriate columns for the test model metrics in order to form predictors, and then we obtain the mean squared error. Next, we look at all of these errors, and we want to find the one that is the smallest. And we see over here that the smallest model is the one that has, the best model is the one that has 6 variables. So then we go ahead and print the coefficients for this model. Finally, we want to perform forward selection, backward elimination, and stepwise regression on the validation set. Then we want to choose the best model from each group on the training set and predict on the validation set. Using the validation set, we want to choose the best model using the root mean squared error. In this case, I'm going to use the step function since it has a predict option, while the reg subset does not have a predict option, so it is more tedious to predict using reg subset. We start by splitting the sample into a validation part and a training part. Next, we fit the model using the LM function. In order to perform backward elimination, we use the function step on the previously estimated model, and then we specify the direction backward. The summary function gives us the model with the variables that were selected in this model. We predict from this model. Notice that we predict using the estimates from the training sample, but when we do the prediction, we use the validation sample. And finally, we use the library forecast and the function accuracy in order to look at the predicted performance. We see here that the root mean squared error for this model selected by backward elimination is 395.08. Next, we repeat this procedure, but we want to use forward selection. We start again by setting the seed and splitting the sample in a 50-50 split. Now, for model selection involving forward selection, remember that what we do, we start with a model that has no variables in it, only a constant term, and then we add one variable at a time. So first, we estimate a model of salary only on an intercept. This would be the model that has no predictors, only an intercept. Next, we fit the model with all the variables included. And finally, in order to perform forward selection, we use the function step, and we tell R to start with the model with no variables included, and then we tell R to go from a model that has no variables included to a model that has all the variables included, and then the direction is forward. And we run this, And in order to see which variables were selected in this model, we use the summary function. We predict on the validation dataset. We use the estimates from the training set and we predict on the validation set. And then we perform, we want to look at the predictive performance of this model, and using the accuracy function, we see that this model has a root mean squared error of 382 and something. In order to compare this with the previous model, that is the model that was selected by backward elimination, we run again the diagnostics for that model, and we see that the root mean squared error for that model was 395, whereas the root mean squared error for this model is 382. So forward selection provides a better forecasting performance compared to backward elimination. Finally, we want to perform a stepwise regression. We split the sample again into a training and validation portion. We fit the full model, and then we perform stepwise regression by using the function step on the previously full estimated model, and then the direction is both. And using the summary function, we can see which variables were retained in the model. And finally, we predict and we look at the forecasting performance of this model is 395.08. And then just to compare this model with the other two models, I have here the root mean squared error for the stepwise regression. Here I have the root mean squared error for forward selection, and then I have the root mean squared error for backward elimination. I see that the root mean squared error for forward selection is the smallest, so this one is the best model. I also notice that the diagnostics are identical for stepwise and backward elimination. So stepwise regression and backward elimination basically lead to the same variables selected in the model. Of course, something that we could do next is to test pairwise hypothesis testing comparisons in order to see if the difference in the root mean squared error is really statistically significant. We've done an example like that in the presentation following the predictive measures of performance.